very much, Eileen. Can you all hear me? Yeah. It's great to see such a massive crowd here today, and it's wonderful to know that you're all as interested and care as much about climate change as I do. So it's a sort of a momentous occasion, I suppose, this week. It's a good week to be talking about climate change. It's obviously the 24th Conference of Parties in Poland, and it's also pretty much the 10th anniversary of the UK Climate Change Act, which came into force in 2008. And I think it's really interesting, actually, how much momentum is coming to place behind this idea that we need to do something about climate change. What I want to tell you in this talk today really is to sort of tell you about the science, what we can expect from climate change, but a little bit about what people are doing about it and why we should have some optimism about the future. Because I think that certainly when I look at the science, I'm often thinking about sort of doom and gloom and oh no, more impacts. But actually, you know, we should have some optimism. All of you guys are here today listening to me talk. We should have some optimism that we can do something. And I think that one of the greatest optimisms for me, or the greatest hopes for the future, is this new generation. I'll talk a bit later about some of these climate activists, but really people like Greta Thunberg, who has stopped going to school on Fridays every week now. She was able to talk at the Conference of Parties in Poland and said, I will not beg the world's leaders for change. I will tell them that change is coming, whether they like it or not. And I believe that's true, actually, from both my research. I mean, change is coming in terms of extreme weather events, but I also believe that this change is coming in terms of the need to do something about climate change. We obviously heard from David Attenborough as well yesterday in terms of people speaking, the decision makers should be acting. And the UN have provided, for those of you who don't know, and I wanted to flag this up at this stage, a website called actnow.bot. You can go and have a look on that website for things that you can do as an individual to actually start to address some of the issues of climate change. So you may have seen this on the BBC News last night, and it rather stole my thunder with this talk. And those of you observant among you will have noticed that I'm also wearing my global warming stripes scarf. Now this was an idea in terms of communication of climate science, put together by Ed Hawkins, who's a professor in London, and who I work with on some work on historical reconstructions of climate change. So the idea behind this is obviously this warming stripes showing annual global temperatures from 1850 to the present day, 2017. And you can see from this the dramatic warming that we've seen, and particularly in the last 15 years or 20 years or so. You can see there that the last 4 years have been the 4 warmest years on record globally, and we expect 2018 to be the 5th, well, among those top 4 or 5 warmest years on record. So climate is warming, and if you're interested in having a look at these warming stripes or looking at other things that Ed has produced, then you can go to the website link at the bottom there. So we're definitely seeing warming of the climate. You can also see from this animation, again by Ed Hawkins, how close we are getting to the targets that were set by the Paris Agreement in 2015. And you can see how rapidly we're now speeding towards those targets. So in 2017, we're really coming very close to that target of 1.5 degrees. And other scientists, climate scientist friends that I know, say that we would already be there if it wasn't for sulfate aerosols, actually. So the pollution we emit in our cities actually helps to reduce this warming. And actually, if we stop polluting as much, then we may have already reached that 1.5 degrees. So where are we at the moment? So you'll have noticed that there was a very important report came out on climate change in early October, so not very long ago. And that was the special report on global warming of 1.5 degrees. And that's obviously addressing the targets that came out of Paris. Since 1850s or so, we've managed to contribute almost a degree of warming globally as humans. That report said. We're seeing consequences already. I'm going to talk about some of those consequences in my talk. And at the current rate, we're likely to reach this threshold of 1.5 degrees somewhere between 2030 and 2052. So that gives us, and you'll have heard this in the news, 12 years. It probably gives us less than that actually, but certainly 12 years to act. We really need to be decisive now. I think that's the message I want you to take away from this talk. Luckily, past emissions alone do not commit the world to 1.5 degrees. So we can still do something about it, but we really need to act now. And that's what the Conference of Parties in Poland are really talking about this week. You know, how can we actually produce the emission reductions we need to come up with a target of global warming of only 1.5 degrees. So what does living in a 1 degree C warmer world mean? We're already living in a world that's 1 degree, and that doesn't sound very much actually, but I'll show you why it matters in a minute. You know, we're also already seeing dramatic extreme events around the world. So you can see massive flooding in southwest China. That was actually in 2013, and Mexico as well. You can see the Rhine in Germany this summer. It dried out so much with drought that actually you couldn't navigate the river anymore in some of these big ships. Obviously the sounds like that. Can you still hear me? Yeah. The California wildfires as well, very dramatic, likely to increase with warming. But then also thinking about health effects and things like that. So Japan, dramatic heat waves and big number of deaths from heat waves, and air quality as well. So in Canada, they had big issues with air quality this year because of warming. So we're already seeing a number of dramatic effects in our 1 degree warmer world. So do we really want to get any warmer? So I want to go back to basics first, and you'll probably all have heard this already in terms of the greenhouse effect. But the greenhouse effect is something that basically happens in the atmosphere, in the planet. If we didn't have the greenhouse effect, actually our planet would be about 33 degrees cooler than it is. So we need the greenhouse effect. Basically what happens is the sun's energy comes into the Earth and as a shortwave radiation, and it reflects back off the Earth's surface as long-wave radiation. And some of that bounces back out to space, but some of it is actually absorbed by what are called greenhouse gases. So some gases have properties, absorption properties, that allow them to absorb that wavelength of light, and therefore provide warming. What happens, of course, though, when we increase those greenhouse gases in the atmosphere is that we amplify that warming effect. And that's also exacerbated further by the fact that when the atmosphere is warmer, it holds more moisture, and water vapour itself is a greenhouse gas. So we exacerbate that effect through natural feedbacks as well. When we're talking about deniers, and this is a slide from my friend over at UC Berkeley in the States, Mike Weiner. He always says denial is not just a river in Egypt. But it's not rocket science. It's something we've known for a really, really long time, you know, when climate deniers tell you actually carbon dioxide emissions, human emissions of greenhouse gases aren't causing global warming. It's something we've known about for a long time. It's steam engine science. We've known about it since John Tyndall's experiments in 1859, where he measured the radiative absorptive properties of many gases, and you can see some here, basically, and he looked at these and measured their properties and showed that basically some of them, like methane, have very high absorptive properties. Some of them in the middle, water, vapour, nitrous oxides and carbon dioxide have these medium level properties, and some are lower. But basically stating that the atmosphere allows this solar radiation to come in, but checks its exit, and the result is a tendency to accumulate heat at the surface of the planet. Again, there was a paper, again saying, you know, it's steam engine science, another paper called On the Influence of Carbonic Acid in the Air Upon the Temperature of the Ground in 1896. Basically by a guy called Arrhenius. He published a paper stating that a doubling of carbon dioxide in the atmosphere would raise surface temperature by about 5 to 6 degrees above pre-industrial temperatures. Again, that was more than 100 years ago now. And it's interesting because actually the latest assessment report from the Intergovernmental Panel on Climate Change actually came up with their very sophisticated climate models with a very similar figure to what he calculated over 100 years ago now. So they came up with a range of somewhere between 2 and 6 degrees. And we call the climate system's response to a doubling of carbon dioxide the equilibrium climate sensitivity in climate science. Of course, we know that humans are changing the atmospheric composition of the atmosphere, and actually in October this year, carbon dioxide in the atmosphere was at 409 parts per million, and you can see on this graph here that actually naturally atmospheric carbon dioxide is around about 300 parts per million, and we've not seen, basically within the last 600,000 years, carbon dioxide has not been higher than it is today. You can see this massive increase in the last, well, this is 1950. So in 1950 it was slightly above 300, and then it's gone up to 409 today. And we've been measuring carbon dioxide now since 1957, and that's at the Mauna Loa Observatory on Hawaii. And you can see here a steady increase in carbon dioxide, and the little jaggedy bits are basically summer and winter in the northern hemisphere, and that's the drawdown by vegetation when it's growing in the summer in the northern hemisphere. And that causes the ocean to become more acidic, and the ocean also takes up more carbon dioxide, but because of that it becomes more acidic. And as I was saying already, the important thing to note is that not all of these greenhouse gases have the same effect, and actually so it does actually matter how much of these greenhouse gases we put into the atmosphere. They have a different ability to absorb radiation, and you can see some of them have, black carbon for example has a high ability to absorb radiation, but it has a very short lifetime in the atmosphere. This is the lifetime on the x-axis at the bottom here. And actually it's the lifetime in the atmosphere and its ability to absorb radiation coupled with the amount that's emitted that actually matters. And you can see here that carbon dioxide is by far the most important greenhouse gas. Although it has only a medium ability to absorb radiation, it has a very, very long lifetime in the atmosphere, and therefore it's very important. And you can also see here that actually these sulfate aerosols, the things that cause acid rain, actually provide a cooling effect. So I want to go on and talk a bit about the special report on global warming of 1.5 degrees that just came out in October, and a bit about the Intergovernmental Panel on Climate Change. And that was actually formed in 1988, and it doesn't produce new science, so that's an important thing to note. It actually assesses the scientific evidence out there, and every 6 years it produces an assessment report which basically tells you the current state of knowledge on climate science or climate impacts. And there have been 5 assessment reports so far, and the next one's due in 2021. And these are slides from my friend who's a professor over at ETH in Zurich, and she was the lead author on this special report on global warming of 1.5 degrees. And you can see that actually, I mean, this is staggering, I think. I think it's really interesting. So when you look at a report like this, there were 91 authors from 40 countries involved, 133 contributing authors. They looked at 6,000 scientific studies. There were then a number of reviewers who provided 42,000 comments for those poor authors to actually address. And so, you know, this is a really, really detailed, thorough process, these reporting. So it really does look at the latest science. And obviously the 1.5 degree warming report was precipitated by the Paris Agreement. So the Paris Agreement happened at the 21st Conference of Parties, and of course we've got the 24th at the moment in Poland. Actually, we've had one of these every year since 1995, and they result from the setting up of the United Nations Framework Convention on Climate Change in 1992 at the Earth Summit in Rio. And basically this was ratified in 1994, and since 1995, a representative from each country who's in this agreement has met annually. And the objective is to stabilise greenhouse gas concentrations at a level that prevent dangerous anthropogenic interference with the climate system, but dangerous climate change, basically. So we're trying to prevent dangerous impacts of climate change. And Paris agreed that we would try and hold the increase in global average temperature to well below 2 degrees C and pursue efforts to limit the temperature increase to 1.5 degrees C above pre-industrial levels. And that's the reason that we've just had this report on warming of 1.5, is to basically look at the difference between what we can expect in terms of impacts from a 1.5 degree world and a 2 degree world. And the reason that we were interested in this, or the reason they really made they actually came up with these targets, or were able to come up with these targets in Paris, is because in the 5th assessment report of the IPCC, the Intergovernmental Panel on Climate Change, they were able to show that actually there's a direct link between the amount of carbon dioxide in the atmosphere, or the cumulative emissions into the atmosphere, and the temperature, the global temperature anomaly. And so you can basically, there is some uncertainty around this, but actually basically you have a direct link. So you're able to then set targets of carbon dioxide emissions to produce certain temperatures within some uncertainty range. And that means you can then back calculate and actually work out how can we actually reduce emissions, and you can come up with a lot of different scenarios to actually do that, and different pathways for emissions reductions to give you the same temperature target. But of course there's regional implications for this, and this is really important. You know, when we're talking about a 1 degree world or a 1.5 degree world, does that actually mean that it's going to be the same everywhere? Is it going to warm 1.5 degrees everywhere and all of the time? And of course the answer is no. There's much, much stronger warming of land extremes compared to the global average, and that's because when you get soil moisture feedbacks, when you get warming, the soil dries out and it exacerbates that warming effect. So you can see here, for example, changes in temperature of the hottest days are around 3 degrees or something like that for parts of the northern hemisphere, and even warmer or larger changes in the coldest nights for 1.5 degrees. For example, this shows the global warming along the bottom and the Mediterranean warming for the warmest day of the year. You can see that a global warming of 2 degrees would give almost a 4-degree warming in the warmest day of the year in the Mediterranean. So we get much bigger increases in extremes and much bigger increases in over land in particular than the global average. What does this mean then? So this is summer 2018. Yeah, this is basically some satellite images showing Germany, northern Germany, Denmark and Sweden. And you can see here what it looked like in summer. At the end of June, you can see lots of nice green vegetation. Obviously we had very dry conditions, and by the 19th of July you can see all of this vegetation has died out. And that has a massive feedback effect on land surface temperatures. And you can see here what the European land surface temperatures look like going from 1910 up to the current year, 2018. And actually you're just seeing this massive rise in temperatures. So this is standardized on the 1961 to 90 period, but the anomaly was over 4 degrees this summer. So with a 1 degree warming, we're already seeing these massive changes in temperature. The other thing is that you also see the same sort of scaling for minimum temperatures, and I've said that already. You see much larger changes in the minimum temperatures than the maximum, and also something that I'm very interested in, I'm going to talk a bit more about this in the rest of the talk, which is talking about extreme rainfall. So there's a direct scaling between temperature changes and the intensity of rainfall events as well. And so you can see here that actually for something like a 2 degree warming, you get something like a 12% increase in the intensity of rainfall events. And of course this is really important, and we've seen this already in terms of some of the big hurricane events. And again, this guy, Mike Wayner, has done a lot of work on this, looking at basically how global warming has intensified these events. Hurricane Harvey produced over 800 millimeters of rainfall over a few days in Houston last year. And we saw the impacts of Florence as well this year. But there have been a number of scientific papers now showing how global warming has intensified the rainfall associated with these hurricanes, but also made them slower moving. And actually, when we get greater warming at the poles than the equator, you lose that temperature difference, and that actually slows down the jet stream and makes these systems slower moving. So then you can get more stalling of these systems, basically. They're more stationary, so they can sit over somewhere for longer. So that's another issue with warming. So I'd say we're already experiencing highly extreme events in a 1 degree C world, never mind thinking about 1.5, 2 degree, or indeed what we're on track at the moment for, which is probably 3 or 3.5. So I've said already that a warmer atmosphere holds more moisture, and you can see basically this red line here shows the dew point, which is basically how much water you can get out when it rains. For, say, a temperature of 20 degrees, it tells you how much water there is in the air. And you can see there's an exponential relationship, basically, between the temperature and the amount of water that it can hold. And actually, we call this Clausius Clapeyron. You don't have to remember that, but basically, in science, we call that Clausius Clapeyron. And basically, it's saying the water holding capacity of the atmosphere increases by about 7% for every 1 degree rise in temperature. And because basically the dew point really tells you about when it's going to rain, we expect that extreme rainfall is expected to increase at about this rate. And actually we've done some work recently, and I don't know whether Hyde is in the audience, but he's just come over from India. basically confirming that actually around the world we do see this scaling of around 6 or 7% per degree C warming for daily extreme rainfall. So we're expecting that daily extremes will increase with warming at about 6 or 7% per degree. So, you know, that's a reasonable increase under a 2 or 3 degree world. And of course this means that we get increases in extremes. This is over the US. You can see this is actually looking at the percentage of the contiguous US land area where there's more than average, more than normal, I suppose, extremes happening over 1910 to present day, and you can see this big rise in recent years. We also did a lot of studies over the last decade, or almost a couple of decades now actually, looking at the UK in terms of extreme rainfall, and found that over the last 2 decades, a 50-year event, we're looking at multi-day extreme rainfall. It's increased by around 12% across the UK, but over Scotland by nearly 30%. So we're seeing much bigger extremes, and of course they have effects on floods. So floods happen more frequently, and when they do happen, they're more intense as well. But one thing I want to talk about, and something we've been looking at a lot recently, is the fact that actually this relationship becomes even stronger at short timescales. So when we're thinking about very short duration rainfall events, so if you think about back to Thunder Thursday or the Toon Monsoon, you know, something that happens over the space of an hour and a half, a big thunderstorm that dumps a load of rainfall. Actually, these events seem to be increasing at something like 2 times this Clausius-Clapeyron rate. And this is the landmark paper by Geert Lenderink and Erik Maegard in 2008 now, but this red line is 2 times Clausius-Clapeyron scaling, so you don't need to understand all the technical details, but basically you can see that hourly extremes are increasing at about twice the rate of daily extremes with temperature. And that has real implications for society in terms of changes to these type of events and the possible implications for flash flooding and for flooding from rapid response small catchments. We didn't know much about this though, so we've spent, and Eileen mentioned one of my projects, Intense, when she was introducing me earlier, but we've basically spent the last 4 years, I think it is, collecting together a global data set of sub-daily rainfall data, which has just been published in this paper here by one of my postdocs, Liz Lewis. And we've managed to collect over 25,000 station observations across the world, and that allows us to then try and establish what's happening to these type of extremes globally. And this again is a summary that's been put together for the State of the Climate report in the Bulletin of the American Meteorological Society in 2017 by one of my postdocs, Stephen Blenkinsop. And you don't really need to understand all these little things, but basically if you're interested, it tells you about the different methods and the scale of the study, etc. The main thing to take away is basically that we seem to be seeing increases in these sub-daily extremes in different parts of the world. You can see there's some inconclusive studies, but the pluses show increases and these minuses show spatially or temporally varied trends. We seem to be seeing increases in most parts of the world. And actually we were able to show this very, very dramatic increase in short duration rainfall extremes in Australia just this year. We had a paper published in Nature Climate Change this summer, again led by one of my postdocs, Selma Guerrero, where we were able to detect for the first time a change in hourly rainfall extremes outside that of natural variability, so we can detect that there's been a significant change. And that change was above, this is 2 times Clausius-Clapeyron line, this red one here. It's actually very large. So you're looking at 2 to 3 times this rate that we would expect. So when we think back to last week, obviously the massive flooding event in Sydney, there was a big thunderstorm event and 2 people killed in Sydney. We are already seeing more of those events. And with additional warming, we will see more intense events. What's interesting about this, though, is that when we plan for these type of events, we only really think about annual maxima. And actually it matters what happens in different seasons, and actually we're seeing different changes in different seasons in different parts of the world. This is just an example from Sydney, but it shows you that actually we're seeing big increases in extreme rainfall in summer, but we're actually seeing reductions in winter, for example. And this makes a difference actually when we're thinking about flood planning. We need to be thinking about these seasonal changes as well, and not just always relying on this estimate of the annual maximum, which you can see actually is increasing for short duration events and decreasing for longer ones. And that's because of its seasonality. Because if we base our flood planning on these estimates, we basically won't necessarily be planning for this increase in these short duration events. And actually, we could actually see quite different impacts in small catchments to large catchments, which perhaps need much longer duration events to cause a flood, and certainly in urban areas. So we can expect flooding to increase in urban areas and in small catchments, but perhaps not so much in larger catchments because of the increase in evaporation as well that comes with warming. There's also been a lot of work done on changes to the temporal pattern of rainfall with a warmer climate. And again, this is this is by some colleagues from the University of New South Wales in Sydney, but basically finding that we get more intense peak precipitation and weaker rainfall during less intense times. So basically your storm becomes kind of like more peaked and more intense in the intense bits. And I think that's something that we see in other regions as well. But what will happen in the future? So that's the important thing. This is a diagram showing climate model results from a paper by Kendon and Clark in 2011. And you can see, if you're looking at these results, you can see that this is over the UK, expecting quite large increases in extreme rainfall in winter, somewhere between 40 and 60% increases in winter. But actually, when you look at summer, we're really uncertain. The white is basically uncertain, and basically it shows maybe a 20% reduction in extreme rainfall in some areas. And these models that we use to produce these simulations are quite coarse resolution. And of course, the issue with these models is they can't really reproduce the type of rainfall that causes, the type of processes that cause extreme rainfall in summer. So they're not able to simulate these thunderstorm type events simply because they're not at a resolution that can resolve these processes. And actually you can see this here. So we can produce quite well. This is the UK Met Office gauge data, and this is from a climate model which tells us something about rainfall. And we can see that for the winter we actually have a pretty good correspondence between the two. For the summer, however, we're just not producing those rainfall intensities that we see in the observed record, even at the one-day level, never mind going down to the hourly level. So one of the things we've been doing over the last 7 years now, I think it is, or something like that, is to actually come up with some new climate models with which we can make predictions or projections about the future. And we based this on, this is a diagram basically that really got us thinking about this. So this is actually using weather forecast models. This isn't using climate models. This is, you know, the UK Met Office weather forecast model that produces your weather forecasts every day. Basically, we're interested. This is for the Boscastle flood in August 2004. If we used a standard resolution model at 12 kilometres, you can see you just don't produce the intensity of rainfall that you see in the radar observations up here. Whereas if you use a 4 kilometre model, you're starting to get somewhere towards it, and certainly if you use 1 kilometres, you're able to reproduce the intensity of the rainfall and this banding features that you see here. So we're quite interested in that. So we went and we thought, right, okay, well, why don't we run this weather forecast model as a climate model? And that's not as crazy as it sounds, because most climate models are developed from forecast models in the first place, but they're not usually run at such high resolution. And so what we did is we basically ran what we call a convection-permitting climate model. And actually it worked out really successfully. It was very exciting. We ran the model just over this small domain over southern England here, but you can see now it's really something that worked very well, and it enables us to say something about the changes to the duration and intensity of summer convective rainfall, and that's work we did with the Met Office. It's been included in the new UK climate projections, which have just been released on the 26th of November, last week, was it? There's lots of different studies around the world now as well that use these type of models. And the main thing is that these models, like the weather forecast model, are able to produce much more realistic extremes and the duration and frequency of events. And the reason why, one of the reasons why, is because they much better resolve the orography. Now this is the Rocky Mountains, and you can see it's going from 1 kilometre now, down to a more standard resolution climate model would look something like that. So you can see as soon as you lose the orography, you're losing a lot of the process representation within the model. I wanted to show you what the outputs of this type of model look like. Hopefully this will work, which is why I'm using my laptop. Right, so this is from a collaborator over at the National Centre for Atmospheric Research in the US, and they've got a 4 kilometre model which runs over the United States. And the nice thing about these models, you can see, for example, this is June 2006 running for. You can see that every day you get this convection initiation over the Rockies, and during the night it moves downstream to the east from the Rockies. You can also see in a minute a hurricane forming here in the Gulf of Mexico. So, you know, these models are quite interesting. They're able to reproduce a lot of the features that we see in our climate, and able to tell us a lot more about extreme events. Right. So, showing you some of the results that we came up with in this study in 2014, where we ran this first weather forecast model as a climate model over the southern UK. We were able to, for the first time, come up with some estimates of how these very intense short duration rainfall events might change. And so we compared our new weather forecast resolution model at 1.5 kilometres to the projections of change from the standard resolution regional climate models. So they would, for example, be used for all the national climate change scenarios, certainly the last set for the UK climate projections that were released in 2009, but other national scale scenarios for different countries. And you can see that there's a massive difference between the two in terms of the potential changes. And actually they showed that rather than no change, summer rainfall intensities were expected to increase by about 30 to 40% for short duration extremes. This is by the end of the century. And actually hourly events over 30 millimetres, which is an indicator of flash flooding, a flash flood warning threshold for the Flood Forecast Centre, show a 5-fold increase. So they increase 5 times to become 5 times more frequent by the end of this century. And this has now been used to provide revised guidance for UK sewer design for the UK water industry, and I think provided some very useful information. We've also done a lot of work, lots of other work, but some other interesting work that we've done looking at these model outputs has also established that we can expect these events to both be more intense, but also to be longer in duration as temperature increases. And that's important as well, because it means your total rainfall is going to be increased much more than just your peak intensity. One of the interesting things we're also able to do with these type of models, and again this is from Mike Weiner at UC Berkeley in California, is to come up with statements of how much climate change has contributed to current extreme events, and they call this forecast attribution or event attribution. And actually this year they released the first hurricane forecast attribution statement for Florence, and they did this by running a weather forecast model, a standard weather forecast model with observed conditions, etc., as they would normally run a weather forecast model. So they ran an ensemble of forecasts, a number of models, and then they actually modified the forecast by basically taking away the climate change signal to represent a world without climate change. That's really interesting, and the first time it's been done in terms of real-time attribution statements. Before the hurricane happened, they were able to make a forecast of how much the hurricane would have been changed by climate change, by warming. And they stated that they expected the rainfall to be significantly increased by about 50% in the heaviest part of the storm. And this increase is much larger than expected from these 7% per degree warming, these thermodynamic considerations. It would remain at a high category for a longer duration, and it would be 80 kilometres in diameter larger at landfall because of this human warming signal in the climate system. I think all of that is quite sobering, really. That's a 1 degree world. That's something we've seen this summer. So what do we need to do about climate change? I'm sure that a lot of you have come today to listen to the science, but also think about what you as individuals can actually do. And it's clear that we need to take a twin-track approach to dealing with climate change. We need to think about adaptation, which is basically trying to adapt our society to the inevitable impacts that are going to come from a warming climate. So we're trying to prevent the worst from happening. And mitigation, which is basically reducing these greenhouse gas emissions that are going into the atmosphere. So we're going to try and avoid the worst possible effects of climate change by reducing the emissions. And you can see here there's a number of different things we can do in terms of adaptation and mitigation. I mean, some of these adaptation, they're not necessarily just building bigger flood defences, for example. It's all about early warning systems, providing communities with the ability to become resilient themselves, to actually work with individuals and communities to provide that resilience. In terms of mitigation, there's a whole load of things we can do. We can actually become more energy efficient. We can really invest in renewables, etc., etc. So there's lots of things we can do. And actually, the UK Research and Innovation have just put a whole load of money into improving climate resilience in the UK through improving these adaptation measures here. So just talking briefly about the UK Climate Change Act, as I say, I think it came into force in November 2008 rather. So it's just over 10 years now since the Climate Change Act came into force, and it's a long-term, legally binding framework to tackle climate change in the UK. We have a committee on climate change in the UK and an adaptation subcommittee. I don't know how many of you knew that. And they review basically the implementation of climate change adaptation and mitigation within the UK periodically. And the Climate Change Act itself required that our emissions are reduced by at least 80% by 2050 compared to 1990 levels. And we actually have to have a UK climate change risk assessment every 5 years as well, which basically considers what the main risks are to the UK from climate change. The nice thing you can see here basically in terms of, this is from a report by the Grantham Institute, when basically celebrating 10 years from the Climate Change Act, looking at the carbon budgets in the UK. The red line shows the actual emissions, whereas the grey shows what we were targeting to reduce our emissions by. So we're on track, actually. We're on track at the moment to meet this 80% reduction by 2050. And actually, we go through this cycle every 5 years. The first one, the Climate Change Risk Assessment, was in 2012. This then informs a national adaptation programme, which then moves forwards. There's a report on the National Adaptation Programme by the Adaptation Subcommittee, and then there's another evidence report, etc., etc. And we also have this national adaptation reporting as well by companies who can actually report on their adaptation plans. So there are things going on in the UK. We're making progress. The last climate change risk assessment in 2017 found there were 6 priority areas which needed to be addressed in terms of risks. The major one being flooding and changes to coastal changes, risks to communities, business and infrastructure, and the second one being risks from high temperatures to health and well-being. And they're pretty obvious in terms of the risks that I've discussed already. And then there's secondary risks for things like water supply shortages, and that's a particular problem in the southeast of the UK. So what are the differences between impacts at 1.5 degrees and 2 degrees? And this is again coming from this warming report, a special report on global warming of 1.5. Obviously, from what I've shown you already, we can expect less extreme weather at 1.5 degrees rather than 2. I haven't talked about sea level rise at all, but we can expect 10 million fewer people to be exposed to the risk of sea level rise with a 1.5 rather than a 2 degree. But actually we're still going to see some irreversible changes, and I think one of the really sad things is that regardless of what we do, I think we're going to lose coral reefs at this point, and that's quite sad. And as I've said already, at the current rate of emissions, we'll actually reach this 1.5 degrees quite soon, so maybe within the next 12 years. So that's quite a sobering thought. So we need massive and rapid change. So that's something that's really come out of this report. We need to reduce our emissions by 45% by 2030. I mean, that's not very long to reduce our emissions by 45%. And we need to reach net zero by 2050. This is to keep below 1.5 degrees. I mean, it may not be possible to keep below 1.5 degrees. The good news is that we've got all the technology we need. It exists. It's just not at large enough scale at the moment. So what we really need is an unprecedented change in terms of scale. And we need emissions reductions in all sectors. Again, though, to reiterate, we're not committed to 1.5 degrees C yet, so it really makes a difference what we do now in terms of the future trajectory of everyone on this planet. So we've got a countdown to basically how long we've got before we use up the carbon budget for different levels of warming. You can see here, this is from the 5th assessment report. We're really looking at quite short time frames for 1.5 degrees. We've got a little bit longer for 2 degrees, still not very long though, You know, we're talking about 25, 30 years. We've really got to be thinking about changing things right now, today. But I have optimism about it, actually. I mean, you guys will have seen this as well. There's been a massive, massive increase in climate activism within the last, the last few months, but certainly the last few years. There's been protests in Washington over Donald Trump's stance to climate change. Again, there's Greta there on her strike in Sweden. A similar strike last week in Australia. Australian school children all on strike last Friday because of climate change. And this Extinction Rebellion group as well, supergluing themselves to Parliament recently to protest against climate change. We hear this hashtag all the time on Twitter now as well, climate breakdown. I went to a meeting in London 2 weeks ago from the Institute for Policy Research, Public Policy Research, on the implications of environmental breakdown. People are thinking about these things really quite seriously in governments as well. I wanted to finish by saying something about a meeting that I just went to in September. I was very fortunate to be invited along to a symposium that was held at 79 degrees north in the Arctic Circle. And it was a select group of only 45 individuals from around the world, including scientists, business leaders, etc. And it was really interesting. I have to admit that looking at all of these things in my day job, I've become quite despondent at times around the potential impacts of climate change. But this really did give me some optimism and hope for the future. One of the people who was at the meeting was the chief strategist for the Bank of England, Michael Sheeran. And really, I do believe, after talking to a number of people at that meeting, you know, people who are managing $100 trillion pension funds, etc., big financial institutions, really are thinking very, very carefully about climate change and these massive and rapid transitions that are needed in our society through to low carbon futures. And this is in terms of providing new infrastructure, it's in terms of reducing emissions and transitioning through to renewables or other technologies as well. So there's a number of different risks potentially in terms of actually moving through to these new a new society, I suppose. But the financial institutions are really thinking about these. There's going to be disruption from the speed that's necessary to make these transitions through technological advances and government climate policies. But then there's also the physical risks to individuals and assets as well, and investment assets from these extreme weather events that I've already been telling you about. There's a big difference at the moment between the investment needs we need for a 2-degree world rather than the current policy scenario. And actually we need to reallocate, I can't even understand how big that figure is myself, but $26 trillion to achieve the 2-degree target. The important thing is that actually we need to move much more rapidly and much more quickly into green investment. And I think this is where you can all make a difference as well, actually. I gave the same response at the climate question time thing that I did in Leeds the other week. You know, individuals can make a big difference. You know, talk to your pension fund, talk to your banks. I'm talking to the Vice Chancellor of the University tomorrow about divestment in fossil fuels at the University. We need to really be quite vocal about these things. You know, don't invest your money in fossil fuels if you can. We really need to make a change quite rapidly. There is this big move towards green investment. And people who are thinking about investments over decades or multiple decades are really interested in going green because, of course, fossil fuels are on the way out. Fossil fuels are predicted to peak in 2023. Now, I'll believe that when I see it, but that's what I get told by people like Anthony Hobley from Carbon Tracker. And actually, the reason it's so popular still is simply because it's so well subsidised. 78% of US coal is subsidised to be cheaper than renewables. No, that's changing. Renewables are becoming cheaper and cheaper and cheaper. It's going to change. And the good thing, as well, is that policy can assist in the transition, but it can't stop it. Yeah? All the scenarios they've run, even with weak global climate policies, and I'm looking at you, Trump, actually doesn't have any climate policies, but yeah, I mean, you know, so he can't stop it, that's good. Changes can happen really rapidly, you know, this is why we should be optimistic. This is the historic data for photovoltaics, basically, against the World Energy Outlook predictions, and you can see that every single year they've been wrong. Yeah, this is what's actually happened. This is the predictions. They're all wrong. That changes can happen much faster than we expect them to happen. And go and read this Expect the Unexpected report. It's really, really interesting. I'm going to finish here, but basically to reiterate again, David Attenborough gave a great statement yesterday at the Conference of Parties. Climate change really is our greatest threat, I think, and time is running out. Current emissions put us on a warming of about 3 or 3.5 degrees by the end of this century. We're trying to stay below 1.5 or 2 degrees. We're not on target at the moment. We already live in a world that's 1 degree warmer with lots more extreme weather events. That's going to get worse with warming. And I've not even talked about sea level rise, actually, and that's, you know, the big, well, Mike, again, calls it the 600-pound gorilla in the room, actually, because there's so much uncertainty around sea level rise and what will happen. But we can expect it to increase by up to 1 metre by the end of the century, under 3 or 4 degrees of warming. We're not tied into 1.5 degrees of warming yet, but we've got a very short amount of time to do anything about it. And we need to act now. But I do have some optimism because individuals are taking actions, and I think that hopefully that in the financial world will actually force governments to take action as well. So we should be thanking people like Greta here, really, for making a stand. And I do hope that the next generation can start to make a stand about climate change. So thanks very much.